depending on how you set up your variables. So here's how I will do it. Let's say that A is equal to Ash's age, and N is equal to the number of student players. And I actually need more space, so I'm going to erase the triangle inequality on this side. So let's read these sentences very carefully. If Ash plays with the students, the average age on that team will decrease from 12 to 14. So Ash's contribution from the new mean is going to be equal to 2. And if Ash plays with the teachers, the average age on that team will decrease from 55 to 52. So Ash's contribution to the teacher team, so that's going to be 16, because including Ash, there's 16 people, but we're subtracting the students. That is going to be equal to 3, but -3, which is why I swapped it. So let's rearrange these equations. We have A minus 12 is equal to 2n plus 2. And then we have 55 minus A is equal to 48 minus 3n. If we add these equations together, we get 47 is equal to 50 minus n. Pardon me, not 47, 37. So one good life lesson that you pretty much will always learn in a math class is that you should only trust your own logic. And so if I make a mistake, I invite any of you guys to point it out and, let everyone know, because we're here for the truth, not for my ego. So that means that there are 13 student players. No, whoa. Can I solve equations correctly? Just asking for a friend. So this is going to be 43. This is going to be 50 minus n. So n should be equal to 7. All right, so then if n is equal to 7, then A minus 12 is equal to 2 times 7 plus 2, or A is equal to 28. So that would be A. I made a couple of arithmetic mistakes there, so I understand if it was confusing. If you have any questions, please feel free to ask them now. All right, it doesn't look like I'm going to get any, so I'm going to move on. So consider the sequence of positive integers: 1, 2, 1, 2, 3, 2, 1, 2, 3, 4, 3, 2, 1, 2, 3, 4, 5, 4, 3, 2, 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1, 2, and so on. So what is the 25th term in this sequence? So here's the question that I want to ask to understand this sequence. Basically looks like it's going up and then down, and then up and then down, and then up and then down, and then up and then down in this pattern like this. And it's going up by 1 each time. Can you put the number 4 solution back? There you go, Stuart. Let me know when you're done and you're ready for me to move on. Also, I'm not sick, but I do have a cough, so I'm going to mute myself occasionally, just a cough. Cool. Thank you, Stuart. So, since this thing is going up like mountains, and it's going up by 1 each time, let's ask the question, when does each number occur first? So, when does each number occur first? Okay, so let's make a list. N and then first n. We have 1, 2, 3, 4, 5, 6, 7, 8. And the first one appears at the ones place. The it is allowed to be equilateral in the first. Okay, so I got a question for number 3. Sorry for jumping all around, but for question number 3, someone asks, I got 2024 plus 2012. How did you get 2005 for the first case? If so, is that where the case where the triangle is equilateral? Yes, that is the case where it's equilateral. Is that allowed? Yes, it is, because it's isosceles, which doesn't exclude it being equilateral. And it is an isosceles triangle with positive area in that case. So it would count for case 1. Great question. Does that help?
Does that apply to any similar problems as well if they specify that's isosceles? I'm allowed to consider the equilateral case?
You definitely should consider the equilateral case unless they tell you otherwise.
Okay, thank you.
Of course. So going back to this problem, we can see that the first 1 appears at the 1 spot. The first 2 appears at the 2 spot. And the first 3 appears at the 5th spot. The first 4 appears at the 10th spot. The first 5 appears at the 17th spot. And so on. This would be the first 6 is at the 26th spot. I'm not going to extend the list that they gave us. I'm just going to tell you the next one's going to be 37, and then the one after that is going to be 50. And you don't need to make the list longer. You might already be able to see the pattern. Yeah, Q equals question. Sorry. Here's a pattern. Can we find a pattern for this? Well, these are always 1 more than perfect squares, right? This is 0 squared plus 1. This is 1 squared plus 1. This is 2 squared plus 1. This is 3 squared plus 1. This is 4 squared plus 1. 5 squared plus 1. Okay, so the first n occurs at n minus 1 squared plus 1. Okay, that's really great. We're asking what is the 2025th term in the sequence. So if we can just find the biggest number less than the 2025th term, then we'll be good. There's actually a really incredible fact about the 2025th term that you probably should have known this before you taken the test, but I'll tell you why. Whenever you're taking an AMC, you should always know the prime factorization of the year. And what we can see is that 2025 is equal to 3 to the 4th times 5 squared, or 45 squared. So if we plug in 46 into this, n equals 46, when is the first 46? Then we get 45 squared plus 1 equals 2026. So the 2026th term is 46. So that means the previous term is 45. I'm going to give people time to ask questions if they have any. Does anyone need time to, how do we get that equation again? I just noticed the pattern, right? This is 0 squared plus 1, 1 squared plus 1, 2 squared plus 1, 3 squared plus 1, 4 squared plus 1, 5 squared plus 1. And the number that we're squaring is always 1 less than this one. Great. Yeah, there might be another way to do it fast. I was just saying, like, can I get some sort of control on how fast this thing is growing? Sorry, a piece of granola got stuck in my throat. So, is there any other questions on this before I move on? I'm going to assume not. All right, so problem 6 is not that bad if you draw a picture. 5 was mid. I believe, well, okay, this is an opinion. You're free to have whatever opinion you want. I'm not lecturing you. In my opinion, I think every math problem is a beautiful one. I'm not trying to pass judgment on them. They might be easy or hard, but I think they're all nice. So let's draw this. We have an equilateral triangle, and we draw the internal trisectors at each vertex. I can do a little bit better than that. So, okay, we're just gonna have to accept that my drawing is gonna be really bad. I don't want to spend all our time trying to draw this accurately. But I do want to point out that because of symmetry, this angle is equal to this angle is equal to this angle. Yes, and this angle was equal to this angle was equal to this angle. Now, before I do anything else, we got to make sure that we're clear on these triplets of angles being equal just from the fact that this is an equilateral triangle. Because it's equilateral. So I'm allowed to rotate everything by 120 degrees and nothing changes. Does that help? So by rotational symmetry of an equilateral triangle, I'm pretty sure that's not how you spell equilateral, but they don't pay me to spell, okay? They pay me to do math. By rotational symmetry of an equilateral triangle, we have two pairs of congruent triplets of angles. Once we know this, the rest of the problem is going to be not that bad. There's one observation that we can make here that's going to make this problem very simple, but I'm just going to label some of these angles are 20, 20, 20, and 20, 20, and 20. So what if we just highlight this triangle right here? Again, because of the rotational or the reflective symmetry of the equilateral triangle, this is an isosceles triangle, or we could just say that these two angles are 40. And since they're both 40, this has to be 140. So this is 140. No, pardon me, these are both 100. My bad. So these are 100, this is 100, and this other one is 100. Now, we could try to solve for what the other angle is by being smart, but let's just call them all x. And we know that 300 plus 3x is equal to 720. So 3x is equal to 420, or x is equal to 140. So the smallest angle is 100. A lot of people were saying that they were concerned about their score due to their geometry skills. Is there any confusion about how I solved this? Would anyone like any clarification or anything else? So I'm going to give you guys like the rotational symmetry thing means that if I rotate by 120 degrees, I'm going to get the same picture, right? If I just have a regular equilateral triangle, ABC, and I rotate it 120 degrees, CAB, it's going to look the same. It's going to look the same. It's just going to be labeled differently. So that's the fact that we're using here. You could do a lot more work to prove that they're all equal. I don't want to do that. I don't want to waste your guys' time being too thorough. All right, so suppose that a and b are real numbers when the polynomial x cubed plus x squared plus ax plus b is divided by x minus 1, the remainder is 4. When the polynomial is divided by x minus 2, the remainder is 6. What is b minus a? So let's call this polynomial f of x. And what we know is that f of x is equal to x minus 1 times q of x plus 4, and f of x is equal to x minus 2 times p of x plus 6. So what happens if we plug in 1? Then f of 1 is equal to 1 minus 1 times q of 1 plus 4, or f of 1 is equal to 4. Similarly, we're going to get that f of 2 is equal to 6. Yes, I'm basically doing the remainder theorem here without actually saying the remainder theorem. You don't have to do all of this work that I was doing. I just don't know if everyone knows the remainder theorem, so I'm going to try to explain as much as I can. So if we plug in 1, then we get 1 plus 1 plus a plus b is equal to 4. And if we plug in 2, then we get a plus 4 plus 2a plus b is equal to 6. Or a plus b is equal to 2. And 2a plus b is equal to minus 6. So that means that a is equal to minus 8 and b is equal to 10. So 10 minus negative 8 is equal to 18. It's E. You can use synthetic division if you want. There's a ton of different ways to prove this. Year 11, yeah. There's a ton of different ways to prove this. I tried to do it using the least amount of work. But there are always multiple ways of doing it. Basically, somehow we need to determine these facts. As long as we can determine these two things, then we're good. I believe that there will be a recording of this, so if you're still stuck, you can watch the recording. Or perhaps you could sign up for one of my classes where I will talk about these things. So let's keep going. Agnes writes down the following four statements on a blank piece of paper. Statement 1, at least one of these statements is true. Statement 2, at least one of these statements, or at least two of these statements are true. Statement 3, at least two of these statements are false. And statement 4, at least one of these statements is false. Yeah, why is it 8 plus 4a plus b? So can you at least accept this fact? At least how f of 2 equals 6? Which I got from this. Okay, great. So f of 2 is actually 2 cubed plus 2 squared plus 2 times a plus b, right? So simplify this, and it will give you that equation. So I got it by plugging 1 and 2 into this expression. F of x is equal to x cubed plus x squared plus ax plus b. Does that answer your question? Hopefully it does. If you're still confused, you can let me know. Also, okay. Well, I'm going to start talking about problem 8. So if we look at statement 4 first, at least one of these statements is false. That statement has to be true. Because if statement 4 was false, then it would contradict itself. So this one has to be true. Okay, so now, since statement 4 is true, that means that statement 1 is true. And since statement 1 is true, that means that statement 2 is true. And since statement 2 is true, and statement 1 is true, and statement 4 is true, that means statement 3 is false. Like I said, if you're going to use the chat, please just be nice. Don't be judgmental. Yeah, if you know that you need to apologize, then you shouldn't have done it. This is the last time I want to say anything about that. Thank you. So let f of x be equal to 100x cubed minus 300x squared plus 200x. For how many real numbers a does the graph y equal f of x minus a pass through the point 1, 25? So when we do f of x minus a, basically what that does is it just translates the graph over by a, right? So we're just asking how many times can we translate the graph so that it will pass through this point, which is equivalent to asking how many times does the line y equal 25 hit this equation, 100x cubed minus 300x squared plus 200x. Now you might say, Mr. Corbin, this thing looks like crap. Why are we doing this? Well, check this out. If we divide everything by 100 and put it all on one side, then we get 4x cubed minus 8x squared. Oh, sorry, minus 12x squared plus 8x minus 1 is equal to 0. Or let's just call that f of x for now, right? That's the difference between our g of x. That's a difference between f of x and 100 over 4. All right, whatever. Studying the roots of g of x is the same. The number of real roots of g of x is the number of real values of a that will satisfy our equation. Is everyone with me so far? The number of real roots of g of x is equal to the number of times that a translation of f of x will pass through this point. Because all I'm going to do next is determine the number of real roots in a very simple-minded way. So I would like to make sure that everyone's on board. Okay, so let's notice that g of 0 is less than 0. G of 1/2 is equal to 1/2 minus 3 plus 4 minus 1, which is greater than 0. G of 1 is equal to -1, which is again less than 0. And g of 100 is greater than 0. I'm not even going to try to compute it. It's just a really big number, right? It's a really big positive number. But look, I found 4 values where it goes negative, positive, negative, positive. So let's draw a picture of this. All of the hard work is right here. There's a ton of other things that you could do to try to figure it out. But look, at here it's negative, so it's somewhere down here. That's 0. At here, 1/2, it's positive, so it's somewhere up here. At here, which is 1, it's negative. It's somewhere down here. And then over here at 100, it's positive again. So it has to go something like this. And that means that there are 3 real roots that we are looking for. You might be saying, Mr. Corbin, how did you know to try those values? And how did you know to even try this strategy? That's kind of the hard part of this whole problem, is knowing what to do and how much effort to put in. Whenever I see a cubic polynomial, the last thing I want to do is factor it. You know, I went to college for math and I learned how to solve cubic polynomials using a formula, and it's way too much work. And I've tried to factor cubics by hand by being clever, way too much work. If you can get away with not factoring a cubic, then you should try. You should definitely try. So I just plugged in 0, plugged in 1, and I saw that they were both negative. I was like, okay, let's try 1/2. Let's see if it's positive in between there. It just happens to be positive when you try 1/2. Great. We have at least 2 real roots. Then we just see what happens as we go to infinity, right? Or negative. What happens when we go to infinity? Since the coefficient of x cubed is positive, eventually it will tend to positive infinity, and it will be positive somewhere. And so we just need to use the intermediate value theorem that says that if a polynomial goes from negative to positive, then somewhere in between there it has to be 0. So therefore there are 3 real roots. Again, this one was pretty complicated. Does anyone have any questions about this before I move on? Go ahead.
How do you, can we do synthetic division for this?
Maybe, but synthetic division would only really be helpful if we had the roots in the first place, but we don't have the roots.
Okay.
Yeah, I just want you guys to notice I did not find the roots here. All I said is that the roots have to be in between 0 and 1/2 and 1, and 1 and 100. So we still don't know the roots. We just know where they have to be somewhere. And Jason asks, what if the bump was below y equals 25? Then g of x would only have one real root. And the math would tell us that it only has one real root. We wouldn't be able to find values with more than one. There are other techniques that you could use to determine that. For instance, every cubic polynomial does have something like a discriminant, which you can use for like quadratic polynomials and stuff. But the discriminant of a quadratic polynomial will tell you how many real roots it has. There is also something like that for a cubic. Oh, thank you for pointing that out, Lebao. Yeah, I wouldn't recommend any other technique here. If I couldn't make it work using this technique, I would have just moved on, honestly, because cubic polynomials are just hard. It's not worth your time to try to waste your effort on a cubic polynomial. That is my advice. Yeah, if the bump is down here, right? Let's say this was y equals 25, right? Then we would only get one real root, and the math would show that. Yeah. Good question. So problem 10 is not the hardest question. It's actually one of the easiest questions on this test, in my opinion, but it is my favorite. I think this question is extremely beautiful. So a semicircle has diameter AB and chord CD. Okay, it might be easy to factor f of x, but then you have to set it equal to a constant which is not 0. So how does that help you? I mean, you're welcome to try it, but it's not going to necessarily be easier just because you can factor the non-constant part. So this one is going to be super simple. Let's call the radius of the... Oh, wait, sorry, let me finish reading this. A semicircle of diameter AB and chord CD of length 16 is parallel to AB. A smaller semicircle with diameter AB and tangent to CD is cut from the larger semicircle as shown below. What is the area of the resulting figure shown shaded? One interesting thing is that the way that they wrote this problem, it doesn't really say what the diameter of the large and the small circle is, or where the small semicircle is relative to the large one. You can actually redraw this in any way that makes you happy, as long as you have a smaller semicircle tangent to a chord of 1 of 16. And so there are solutions where you can redraw this in a way that makes it nice. We can assume the smaller circle is infinitely small and neglect it. That's a really interesting point, Nelson. That's a really interesting point. I wouldn't necessarily rely on that kind of reasoning all the time, but I think Nelson brought up a very interesting solution. However, I'm going to show one where we don't talk about infinitely small quantities. Let's call this R, and let's call this big R. And our objective is this, which is pi over 2 times big R squared minus little r squared. Now, whenever I see two things that are being combined and squared, I automatically think Pythagorean theorem. You might disagree with me, but you might be saying that's a minus, not a plus. Doesn't matter. Pythagorean theorem. How can we use the Pythagorean theorem here? Well, since this is parallel, we can draw this right here. We know it's length r. And we can draw this right here, and we know that's big R. And we know that since this is a chord and this is perpendicular to the chord, that this bisects the chord, so this has to be 8. So little r squared plus 8 squared is equal to big R squared. So r squared minus little r squared is equal to 64. So our objective is pi over 2 times 64 equals 32 pi. Now, again, Nelson pointed out you could actually assume that little r is equal to 0, and that would force big R to be equal to 16, and we would still get 32 pi. that involves a very, yeah, but they didn't say that the chord couldn't be the diameter. What they should have said is that a smaller semicircle with positive radius. If they wanted to exclude what Nelson noticed, then they should have said this. Yeah. So, however, that is, the big one won't be infinitely small. And we can come up actually with some sort of relationship between big R and little r, what they have to be, according to this right here, right? Big R is equal to the square root of 64 plus r squared. So nothing breaks if little r becomes 0. There's no discontinuities. Again, I want to point out that comes from a very careful reading of the problem that may or may not help you in the future. All right, I'll stop yapping about that. The sequence 1, x, y, z is arithmetic. The sequence 1, p, q, z is geometric. Both sequences are strictly increasing and contain only integers, and z is as small as possible. What is the value of x plus y plus z plus p plus q? So the first way of writing the first sequence, we could call it 1 plus d, 1 plus 2d, and 1 plus 3d. The second sequence we can call 1 p squared, and p cubed. So p cubed is equal to 1 plus 3d, but it's kind of hard to find a cube that satisfies these equations. It's actually much easier to say that d is equal to p cubed minus 1 over 3, and we can find the smallest p that makes this an integer. If p is equal to 4, that will force this to be an integer, and d will be equal to 21. So if p is equal to 4, then we have 1, 22, 43, and then the last one is 64. Down here we have 1, 4, 16, and 64. 1 plus 4 plus 16 plus 22 plus 43 plus 64 is equal to 149, which is E. I'm pretty sure. Let me check my notes to make sure I'm not lying. Yeah. Okay. Can I show 10 again? Yeah. I will leave this here for a moment. Any other questions before I go on? If guess and check works, then you shouldn't do more work than you need to do. Like, I'm assuming that all of you guys have lives outside of doing math problems. So my advice is always to try to find the route of least resistance. Take screenshots every time he does a question. We can wait a little bit. You know, people are trying their best. Can I move on? Well, thank you, Eileen, but I was asking Stuart.
Yeah.
Thank you, sir. All right, I'll leave 11 up, though. So Carlos uses a 4-digit passcode to unlock his computer. In his passcode, exactly one digit is even, exactly one possibly different digit is prime, and no digit is 0. So how many 4-digit passcodes satisfy these conditions? One thing I want to point out is the not even, not prime digits, and not 0. The only digits that satisfy that are 1 and 9. Okay, so let's just keep that in our back pocket for now. The only digits that are not even, prime, or 0 is 1 and 9. Okay, and in his passcode, exactly one 4-digit is even, exactly one digit is prime, but it could be different. So let's listen to two cases. Case 1, we have a 2. And case 2, there is no 2s. Right, and so all right, let's look at this. If we have a 2, that is also the prime number, right? So if we have a 2, then for this one, we have 4 spots the 2 can go in. And then for each of the 3 other digits, we have 2 options. It's 1 or 9, 1 or 9, 1 or 9. So there's 32 options for case 2. How I did it was that the geometric sequence must be 1, 3, 9, 27. Otherwise, the arithmetic sequence with 4 terms would not have it. Emily, you might want to check the logic on that. I don't have time to go through why it's wrong, but I know that my answer is correct, and I am not sure that your logic is solid. Yeah, because 27 minus 1 is not divisible by 3. No worries. So now for this one, if we have a 2, oh wait, sorry, I put that on the wrong case. Sorry, this is 4 times 2 squared, 4 times 2 cubed, which is 32. Let me zoom in a little bit. So now let's say we have no 2s. Okay, we have to choose the even digit where it goes. And there are 3 possibilities for the even digit if it's not 2 or 0. Then we have to choose the prime digit and where it goes. There's 3 options left, and there's 3 for its spot, and there's 3 options for what its value is. Now, we have 2 more digits. They can either be a 1 or a 9 and a 1 or a 9. If we multiply all of these together, we get 432. If we add up our cases, then we get 464. All right. So in the figure below, any questions about this one before I move on?
Wait, I do have a question. Can you redo it?
Yes. So one thing you need to notice is that the only digits that are not even, not primes, and not 0 are 1 and 9. So if we've exhausted all the evens and all the primes, then the only choices left we have for a digit is 1 or 9. Now, unfortunately, exactly 1 digit is even and exactly 1 digit is prime. There's some overlap in those cases, right? 2 is the only even prime, so we have to split it into 2 cases where we have a 2 in our passcode or we don't have a 2 in our passcode. If we have a 2 in our passcode, there can only be 1 2 because there's only 1 even number and there's only 1 prime. There's 4 spots that we can place the 2. And then for the other 3 digits, we have to decide if they are a 1 or a 9. And so we have 4 times 2 cubed options, which is 32 total possibilities. Now, let's say we have no 2s. Then if we have no 2s, then we can't use a 2. Let's pick where the first even number goes. The even number, we have 4 spots that it could go in. And there's 3 possibilities for what it could be. It could be 4, 6, or 8. Next, let's pick where the prime goes. Since 1 spot is already taken by an even, we have 3 more spots for the prime. Once we've picked where the prime goes, we have 3 possible values for the prime. It could be 3, 5, or 7. Once we've done that, we have 2 more open spots. They either need to be a 1 or a 9, so there's 2 options each. And that is how we get the counts for each of these cases.
Wait, how did you get the extra, like, 4 and 3?
So here, this one is even, right? Even spot. And then this is even number. Then this is prime spot. And then this is prime number. And then these are the final digits, right? Does that help? Okay, cool. Thank you. All right. So in the figure below, the outside square contains infinitely many squares, each of them with the same center and sides parallel to the outside square. The ratio of the side length of a square to the side length of the inner square is k, where 0 is less than k is less than 1. The spaces between squares are alternately shaded as shown in the figure, which is not necessarily drawn to scale. The area of the shaded portion of the figure is 64% the area of the original square. What is k? Let's call the original square side length a. So we have a squared minus ak squared. But then we have, or let's just say a squared k squared. Then we multiply both sides by k again and add it back. So that's a squared k to the fourth. Then we multiply both sides by k squared again and subtract it. That's a squared k to the sixth. And so on in this fashion. Let's call this sum S. In order to compute this sum, I am going to multiply it, both sides, by 1 plus a squared k squared. Or sorry, just a squared k squared. So a squared, or no, I'm just going to multiply it by k squared, sorry. So k squared S is equal to a squared k squared minus a squared k to the fourth plus a squared k to the sixth minus. Now what happens when we add these? We get an a squared here, but this cancels, this cancels, this cancels, and all these cancel. And so we're just left with 1 plus k squared times s. And so s is equal to a squared over 1 plus k squared. If 0 is less than or equal to k is less than or equal to 1. Okay, and actually we could put an equality here, but it doesn't matter. So this is a really powerful trick called the geometric series summation. This is one thing that I like to do in my classes is I like to put stars next to concepts if I think that they are cool, and I like to put dollar signs next to concepts if knowing them can get you better jobs. So I would give this formula 2 stars and 2 dollar signs because it's a very powerful and important formula. It's not the most powerful or the most important, but it is powerful and important. All right. So, oh, do you have a question?
What is A and K?
We don't know yet. We don't know those values. Good question. So now they tell us the ratio of. Sorry. Wait, my friend. Let me keep talking. Let me keep talking. So the area of the shaded portion of the figure is 64% of the area of the original square. So S is the shaded area. So you have a squared over 1 plus k squared over a squared is equal to 64 over 100. Oh, what it represents the side of the square. Does that help? A is the side of the square. Where did the plus 1 come from again? Because we're adding up both sides. So s plus k squared s. What's k? K is a number that they told us. We have to solve for it. Go ahead.
So the way I did it is that
I'm not asking for explanations of how you did it. Any other questions before I keep going? We have a plus 1 because we are adding the right side as well as the left side. So s plus k squared s is 1 plus k squared s. Awesome. So now we take the ratio of a squared over 1 plus k squared over a squared. And so we have 1 over 1 plus k squared is equal to 64 over 100, or 64k squared plus 64 is equal to 100, or 64k squared is equal to 36, or 64k squared is equal to 36 over 64. Take the square root, we get k is we're going to take the positive square root is equal to 6 over 8, or 3/4. So what is k? K is 3/4. which is D. All right, any questions about this?
Can you keep it on for a few
Yes, sir. Can you go over the left side of the screen again? Okay, so this is the shaded area divided by the total area is equal to 64%. That's what they said right here. That's the left side is this sentence, and then I'm just solving for k squared. The a squareds cancel out in the ratio. Any other questions? All right, so actually, let's take a 5-minute break. No, actually, let's do this one first, and then I'll give you a break. 6 chairs are arranged.
Question 13, like the problem of still.
All right. 6 chairs are arranged around in a table. 2 students and 2 teachers randomly select 4 chairs to sit in. What is the probability that the 2 students will sit in 2 adjacent chairs and the 2 teachers will also sit in 2 adjacent chairs? So let's draw a picture. Let me know when I can scroll down. I would really like to have some of the screen space back. So we have 6 spots. So the total number of ways to sit 4 people in 6 chairs is 6 times 5 times 4 times 3 times, yeah, okay. And that is equal to 360. Now the number of good ways to seat these people, let's first seat the teachers in adjacent chairs. Okay, so when we seat the teachers in adjacent chairs, there is going to be 6 possible ways to do that, right? So the number of good ways, first we sit the teachers, right? So let's say we pick teachers in these. So the teachers are sitting in these adjacent chairs. Now we need the students to sit in adjacent chairs. So we could do this or this or this. So that's 3 options. And once we've chosen the pairs for each the students and the teachers, then we have to talk about the number of ways they can sit in them. So there's 2 ways for the teachers to sit in those chairs, and there's 2 ways for the students to sit in those chairs. Okay, so what we have for our probability, that is going to be 6 times 3 times 4 over 6 times 5 times 4 times 3. Cancel, cancel, cancel. So that's 1/5. That's B. All right. I know it's a long time to sit down. Come back at 8:02, and we'll keep talking about the test.
I just have a question.
I got to use the bathroom, my friend. Hold All right, everyone. All right. You ready to keep going?
I have a question.
Yes, sir.
How do you get the total and the good?
Well, where you have to seat 4 people, right? How many options do we have for the first person to sit down in? Emerson, I'm just going to stop you right there. I'm not asking for explanations. Unless you have a question, I don't need to hear from you. So, we have 6 spots for the first person. 5 spots for the second person, 4 spots for the third person, and 3 spots for the fourth person. All right, and for good, we have to pick which adjacent pair of seats the teachers are going to be put in. So this is where the teacher seats are. Once we have the teacher seats, then there's 3 possibilities for the adjacent seats that the students are going to sit in. So the students sit here. And then for this one, this is the order of the teachers where they're sitting in their adjacent spots. And this is the order of the students. I can't stay on this one forever because we still have 11 more questions and I'm not going to explain every problem twice. So, for instance, this one takes a little bit of work and I need some time to explain it. I'm not going to explain it more than twice or more than once. So I really need you to ask your question, but your question cannot be, can you explain the whole thing again? Because we have less than an hour. So in the figure below, ABEF is a rectangle. AD equals DE, AF equals 7, or AD is perpendicular to DE, AF equals 7, AB equals 1, AD equals 5. So let's call this X and Y. So X plus Y is equal to 5. Due to vertical angles and the fact that this is a part of a rectangle, we know that triangle ECD is similar to triangle ACB. And according to the Pythagorean theorem, CB is the square root of x squared minus 1. And so then EC is equal to 7 minus the square root of x squared minus 1. Then, according to similar triangles, 7 minus the square root of x squared minus 1 over x. So big hypotenuse over little hypotenuse is equal to hypotenuse over side. So that's x. 5 minus x. Oh, this one is equal to small egg over small egg. So 5x over the square root of x squared minus 1. Now this thing sucks. It's really ugly to look at. Let's try to rearrange it. So we get 7 square root x squared minus 1 minus x squared plus 1 is equal to 5x minus x squared. This cancels, and so we have 7 square root of x squared minus 1 is equal to 5x minus 1. If we square everything, then we have 49x squared minus 1 is equal to 25x squared minus 10x plus 1, or we get 24x squared plus 10x minus 50 is equal to 0. I am going to skip the quadratic formula and tell us that the positive root for x is 5/4, and that means that according to the Pythagorean theorem, BC would be 3/4, and so the area is going to be 1/2 times 1 times 1 times 3/4, which is equal to 3/8. So the answer is A. Any questions about that before I move on?
Just can you put the screen on for like a little more?
My friend, I'm going to insist that you start taking screenshots if you do this every time. So there are 3 jars. Each of the 3 coins is placed in one of the 3 jars chosen at random and independently of the placements of the other coins. What is the expected number of coins in a jar with the most coins? So
Wait,
first,
excuse me.
yes.
For the last problem, how do we know it's a 3, 4, 5 triangle?
Well, we said that this is 5/4, right? We don't know it's a 3, 4, 5 triangle. I used the Pythagorean theorem.
Oh, okay.
5/4 squared minus 1 squared, and then we take the square root.
Okay.
Good question, though. Any other questions before I move on? I don't want to go too fast. All right. So there are 3 jars. Each of 3 coins, oh, I already read this. So let's assume that we can tell the difference between all the jars and all the coins. It's just going to make our life easier. So the total number of placements is equal to 27. Now, how many ways can we have most be 1? There's going to be 6 ways of doing that. If we can tell the difference between all of the coins and all of the jars, then we have to put each of the coins in a different jar. So there's 3 choices for the first coin, there's 2 choices for the second coin, and there's 1 choice for the last coin. So this is equal to 6. Now, let's try the other case where the most is 3. Okay, in order for the most to be 3, all 3 coins have to go in 1 jar. So there's only 3 possibilities. That means that the most is 2 is 27 minus 6 minus 3, which is 18. So the expected value of most coins is going to be 1 times the probability of getting that situation, plus 2 times the probability of getting that situation, plus 3 times, I'm going to erase some of the work here when I have a moment, plus 3 times the probability of getting that situation, which is 3 over 27. Sorry, it's kind of hard to see here, but I'm running out of space. So we have 6 over 27 plus 36 over 27 plus 9 over 27, which is I want to say 51 over 27, which is the same as 17 over 9. So that's D. That one is definitely hard. I wouldn't be surprised if a lot of people struggled with that one. Is there any questions on it before I move on? Is that a yes or a no? I'm going to assume that's a no. All right, so let n be the unique positive integer such that dividing 273,436 by n leaves a remainder of 16, and dividing 272,760 by n leaves a remainder of 15. What is the tens digit of 15? So the reason that I pronounce it that way is because I have a regular person brain and I get jumbled up with big numbers like that. So in the name of that, I'm actually going to write it like this. 273,436 minus 16 is a multiple of n. So I'm going to say big N times little n. And 272,760 minus 15 is also a multiple of n. So I'm going to call that little m. This number right here is 273,420. And this number right here is 272,745. Now, we would like a 2-digit number dividing both of these things. Let's look at the greatest common divisor of these 2 numbers right here. Right? So now you might be like, Mr. Corbin, how do we actually compute that greatest common divisor? Those numbers are huge. I don't want to factor those, and I certainly would never ask you to factor those. Is there some other technique that we can use? Well, there is. I want to use a fact that's super powerful. So this is just a fact. The GCD of A and B is equal to the GCD of A and B minus A. And so then we can extend that to be the GCD of A and B is equal to the GCD of A and B minus K times A. So we can multiply A by any whole number and subtract, and it will still be the same GCD. The reason that the GCDs are equal is because adding or subtracting two numbers doesn't change the common divisors that they have. And so it doesn't change their greatest common divisor. All right, so that being said, we can just subtract here. So this is equal to the GCD of 273,420 and then 273,420 minus this number. So we are going to get, I want to say 600, no, more than that. Let me check my notes. I don't want to do this mentally. I will be accepting help from the chat on how to subtract this. I don't remember what it was off the top of my head. It's 675. Okay. Okay, and then we can subtract 675 a ton of times here. I'm not going to do all the math to tell you how many times we subtract it, but we end up with 675 and 45 at the very end. Okay, and 45 is a multiple of this, or this is a multiple of 45, so the GCD is 45. That would mean that the tens digit is 4. This technique right here is called the Euclidean algorithm. We use this technique right here. We can subtract the smaller number from the big number as much as we want without changing the greatest common divisor. So it's kind of a fact in number theory that I would usually take a whole day to prove. So that's why I just wrote it down as a fact. So I'm just subtracting the smaller number from the bigger number until I get some numbers that are really small. So 273 minus 420 and minus 272, 745, that would be equal to 675. And then let's see exactly how many times we subtracted 675. So 273,420 minus 45 divided by 675. So now 273,420 is equal to 405 times 675 plus 45. So we can delete this number and just replace it with the remainder. Yeah, and just use the remainder. All right. Any other questions before I move on? All right. So problem 18 is about one of my favorite topics. I love my job because I get to talk about the harmonic mean like every other week. So the harmonic mean of a collection of numbers is the reciprocal of the arithmetic mean of the reciprocals of the numbers in the collection. For example, the harmonic mean of 4, 4, and 5 is 1 over 1/3 of 1/4 plus 1/4 plus 1/5. What is the harmonic mean of all the real roots of the 450th degree polynomial? Now here, this notation, I'm super glad that they put this notation on the test. This means that we are adding up or multiplying each of these values from k goes from 1 to 2025 of k times x squared minus 4x minus 3. Now, I want to talk about something called Vieta's formulas. And those say that if we have something like x squared plus bx plus c is equal to x minus alpha times x minus beta, then that means that b is equal to minus alpha plus beta, and c is equal to alpha times beta. So I could justify this, or I could just keep going, and it depends on how many people have seen this fact before. Who is completely unfamiliar with what I am doing here? Okay, so let's back up a little bit. If we have some sort of quadratic polynomial, ax squared plus bx plus c, the dream is to be able to factor it like this: x plus alpha, or a times x plus alpha times x plus beta. If we multiply that out, we get a times x squared. Oh, sorry, not plus. These should be minus signs. We get x minus alpha plus beta times x plus alpha beta. Is anyone confused at least how I wrote down this line? We don't necessarily know A, B, C, or alpha or beta. We just know they have these relationships. Okay. So by comparing coefficients, and we get bx is equal to minus a alpha plus beta, and c is equal to a alpha beta. And so minus b over a is equal to the sum of the roots, a plus b, or alpha plus beta, and c over a is equal to the product of the roots. Anyone confused so far? These are called Vieta's formulas, these two equations right here. All right, if you're confused, I don't know how much more I can tell you, because this is standard multiplying out binomials. So if you haven't taken an algebra class yet, then, oh, it's just this times this.
No, what's that symbol?
It's alpha. All right, any other questions? Okay, so if we have these two expressions, is there any way that we can express the reciprocals of the roots in terms of the coefficients of the polynomial? Pardon me. So there is. It turns out if we do alpha plus beta divided by alpha times beta, we get 1 over beta plus 1 over alpha. But according to Vieta's formulas, this is minus b over c over a. That is equal to minus b over c. So minus b over c is always going to be equal to the sum of the reciprocals of the roots. Even if we don't know the roots, but we know these two coefficients, then we're good. So the sum of the reciprocals of the roots of the I'm erasing Vieta's formulas because I need more space. The sum of the roots of the reciprocals of the roots of all of these are going to be the same, because it actually doesn't depend on k at all. So let me, b equals minus 4, c equals minus 3, so minus b over c is going to be equal to minus 4/3. So all of these polynomials may have different roots, but their sum is always going to be minus 4/3. Okay, and so we have 2025 times 2 real roots, and their sum of their reciprocals is going to be reciprocals is going to be 2025 times minus 4/3. So the harmonic mean is going to be 1 over 2 times 2025 times 2025 times minus 4/3. And that is equal to, okay, so this cancels, this cancels, this cancels, this has a 2. We get minus 3/2, which is B. Yes, you should be able to. I will ask my boss to make sure that the recording is made available to you guys as well, just so that it's not difficult. Besides Vietta's formulas and how they come into existence, is anyone confused about how I solve this? It's all right if you are. We're still making good time. If we finish early, then I will also go back and talk about specific questions that people have. So if you don't want to ask your question now, then we'll come back. We can come back to it later. Let's look at problem 19. So problem 19 is actually really cool. An array of numbers is constructed beginning with the numbers minus 1, 3, and 1 in the top row. Each adjacent pair of numbers is summed to produce a number in the next row. Each row will begin and end with the numbers 1 and minus 1 respectively. The first 2 rows are shown below. If the process continues, one of the rows will sum to 12,288. In that row, what is the third number from the left? You solved it with 5 seconds left? That's cool. So let's look for a pattern in the row sums. Here the row sum is 3. Here the row sum is going to be 6. Here the row sum is going to be 12. And what we can see is actually, it should remind you of Pascal's triangle, because every number gets added twice to the next row. That means that the row sum is always going to double. So what that means is we need to say that 12,288 is equal to 3 times 2 to the k for sum k. I'm going to skip the work. We're going to get k equals 12 after dividing. Okay, so we need to look at the 12th row. I'm going to remake the 12th row. I'll rewrite this here. I'm going to remake the 12th row, and we're just going to look at it. So 2 to the k times 3 is equal to 12,288. Implies k is equal to 12. So we need 13 minus 1s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then it goes 3, 2, 1, 0, -1, -2, -3, -4, -5, -6, -7, -8. Oh, and then we're going to need a -9 here. I guess we'll make this a -1 and this a -10. We might need those. So then we add these two. This is going to be 5, 3, 1, -1, -3, -5. Oh, look at that. It's going down very predictably. Oh, wait, whoa. 2, 3, 1, -1, -3, -5. Yeah, okay. -7, -9, -11, -13, -15, -17, -19. In that row, what is the third number from the left? What the heck did I mess up? Yes, because this should be a 1. -1s. Oh. Should have wrote it like this, actually. Minus 3 minus plus 3 plus 2 1 0 minus 1 minus 2 minus 3 minus 4 minus 5 minus 6 minus 7 minus 8 minus 9 minus 10, and then we have 1, and then 1 plus 3 is 4, 4 plus 2 is 6, 6 plus 1 is 7, 7 plus 0 is 7, 7 minus 1 is 6, 6 minus 2 is 4, 4 minus 3 is 1, 1 minus 3 is minus 3, minus 3 minus 5 is minus 8, minus 8 minus 6 is minus 14, minus 14 minus 7 is minus 21, minus 21 minus 8 is minus 29, and I think that is it, actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, wait, it starts at 0, so this would be 12. So it's minus 29. Sorry, because it starts at the 0. Any questions about that before I move on? So, let's see. I kind of want to do them out of order now, with the easiest first and the longest last. Does anyone object to me doing it out of order with easiest first and longest last? No one cares if I do it out of order? Okay, then I'm going to do it out of order. So for this one, we're just going to construct a maximal, meaning can't make it bigger. Subset. And if you're really mathematically minded, you might want to prove that all the maximal subsets have the same size. However, let's not do that. So one way of doing it is you could do all the odd numbers. And that would be sum free, because odd plus odd equals even. But if there's no even numbers, then the size of this would be 10. And we can't add anything to this. There's no way to add anything to this to make it sum free. Now, another way of doing this is you could do 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. All of these would also be sum free because 11 plus 12 is greater than 20. So they can't add up to anything more. This would also be 10. Like I said, you could do a ton of work and prove that it is impossible to go over 10, that all the maximal subsets will have a size at least 10. However, I'm going to say that on a test, once you have come up with one of these two examples and you struggle with a little bit to come up with something bigger, then you should just circle 10 and move on. The proof that it can't be larger than 10 is really annoying, and it's not useful for us to go through it. All right, so another one.
Wait, can you go back?
Yeah.
Little.
I'm trying to go fast though, my friends. Just write down one of these examples. Yeah, we're going to use Descartes' theorem for the next one. But you spelled his name wrong. It ends in an S. It's all right. He's not a. We also spelled his name wrong because it looks like this. But yeah. All right, I'm going to go down. So a circle of radius r is surrounded by 3 circles whose radii are 1, 2, and 3, all externally tangent to the inner circle and tangent to each other, as shown in the diagram below. So what is r? So for this one, I want to use something called Fermat's little theorem. Or sorry, not Fermat's little theorem. So Descartes' 4-circle theorem. And so I just want to say, if I have a circle and its radius is R1, then K1, which is the curvature, is equal to 1 over K1. Or let's say this is Ri, it's Ki is 1 over Ki. Here's my opinion of Veritasium. He is really good at being the third person to make a video on a topic. But I did not learn about this from Veritasium because Veritasium has never made an original math video in his whole life. He makes very good math videos, but he's never made one about something that someone else hasn't already made it about. So Descartes' four-circle theorem is really cool. I'm only going to talk about a specific case of it, but it doesn't really matter that much. So here we have F1, or sorry, let's say the curvature here is K1. So that's 1 over 1. The curvature here is 1 over 2, K2. And the, 1 over 3. Wait. I've labeled this all wrong. It doesn't really matter how you label it, but I want it to be accurate. So K3 is 1 over 3. K2 is 1 over 2. K1 is 1 over 1. And let's just call this K for this curvature. So Descartes' four-circle theorem says that if we have four circles that are mutually tangent like this, then the square of the sum of their curvatures is equal to twice the sum of their squares. This is a super powerful formula. Oh, I'm messing this up. It's a super powerful formula, and it's actually, it kind of looks random the first time you see it, but there's a ton of formulas that look a lot like this. It's actually not very unique. There's something going on here, which is really cool. Something really cool here going on. And I encourage you to keep going. If you would like to see more theorems like this from someone who the math videos are not that good compared to Veritasium, and he kind of seems like a crazy guy, but he actually has a ton of really good formulas. N.J. Wildberger talks about this and a lot of other formulas that are similar. He's kind of a crazy guy, don't get me wrong, but he also talks about good math, and he has a lot more to say about this. So we can just plug all this into our equation. So we have 1 plus 1/2 plus 1/3 plus k squared is equal to 2 times 1 squared plus 1/2 squared plus 1/3 squared plus k squared. If we do that and rearrange it, then we get the equation k squared minus 11/3 k minus 23 over 36 is equal to 0. And so that means that k is equal to 23 over 6 or minus 1 over 6. Now, what does this mean? What does this mean? It would be negative if all three of the other circles were inside this one. So the negative corresponds to a circle with radius 6. So its curvature is 1 over 6, right? Outside the other three. So sometimes they can be positive or negative curvatures, depending if it's on the inside or the outside. But that doesn't matter that too much to us. We're going to say that r is the absolute value of 1 over k, so it's either equal to 6 over 23 or 6. We are looking for the smaller value. That's the one that's on the inside, not the outside. And so we would get b, 6 over 23. How are you supposed to solve this in less than 2 minutes using something other than Descartes' circle theorem? You're not supposed to solve this in less than 2 minutes using something other than Descartes' circle theorem. Descartes' circle theorem is the fastest way to solve this. It's something that you should know ahead of time. There's lots of other cool formulas like this, and curvature itself is a very fascinating concept. Let's move on. I want to talk about 24, and then let's go back and do 20, 23, and 25. The only reason that I skipped these three for now is just because they involve a lot of algebra with annoying geometry. So, call a positive integer.
Can you keep it there at 22 for like I just still have a little to write down.
Okay, so a positive integer, call a positive integer fair if no digit is used more than once, it has no zeros, and no digit is adjacent to two greater digits. For example, 196, 23, and 12,463 are fair, but 1,546, 320, and 3,400, 322 are not fair. How many fair positive integers are there? So let's come up with some cases. So case 1 is the greatest digit. Oh, wait. So one thing I wanted you to notice about all fair digits is they go up and then they go down. Their digits go up, and then at some point they go down, down, down again. Okay, so that's why I'm going to break the cases up by which number is the greatest. So we have case 1, 1 is the greatest. Case 2, 2 is the greatest. All the way down to case 9. And 9 is the greatest. Okay, so for each case, let's say we're in case I. We need to consider each digit less than I. Okay, so it can go on the right, the left, or be excluded. So that means that we have to make 3 to the I minus 1 choices. And so if we sum up all the choices that we have to make, we have 3 to the 0 plus 3 to the 1 plus 3 squared plus ... all the way down to 3 to the 8th power. This is going to be the number of fair numbers. You might recognize this as a geometric series. If we multiply this by 3 minus 1, we get twice the sum that we're looking for, but we also get 3 to the 9 minus 1. So what we're looking for is g is equal to 3 to the 9 minus 1 over 2, which comes out to 9,841. That one is kind of tricky, and I solved it by splitting up the cases in a very sneaky way. Is there anyone who's confused about this before I go on to the remaining 3 problems? I tried to present a solution that doesn't involve that much work. So you have a question, or are you ready for me to move on? Yeah. So each fair number, it has to go up and then down, and it has a unique maximum. Because if it ever dips like this, it won't be fair, because that would no digit is adjacent to 2 greater digits. So each case is what is the largest digit in each number. So for instance, here we have 1, and then 1, 2, or 2, or 2, 1. And then, so that's 3. That corresponds to this 3 to the 1. Then case 3, we have 1, 2, 3, 1, 3, 2, 2, 3, 1, 2. We can't have 2, 1, 3 though. And so I'm not going to write them all down, but case I, we need to consider each digit that's less than I. And for each digit, we don't have to use all of them. So there's three possibilities. It either goes on the right side of the maximum, it goes on the left side of the maximum, or we just simply don't even use it in our number to begin with. So that gives us 3 to the I minus 1 choices. The reason it's I minus 1 is because it has to be strictly less than I. Yeah. That's why it's a geometric sequence. Awesome. All right, so I'm going to start at problem 25 now. A point P is chosen at random inside square ABCD. Oh, sorry. Once there's too many annotations in the document, I guess my computer likes to freak out. When I erase things too quickly. So let's try this. So a point P is chosen at random inside square ABCD. The probability that AP is neither the shortest nor the longest side of APB can be written as A plus B pi plus C root D, where A, B, C, and D and E are positive integers, and the GCD of A, B, C, and E is equal to 1, and D is not divisible by the square of any prime. What is A plus B plus C plus D plus E? So let's draw a picture. A, B, C, D. So P is chosen at random. And we're interested in A a lot in this problem. So I'm going to draw a semicircle centered at A, passing through B and D. Okay. And P is neither the shortest side nor the longest side. So if AP is the shortest side, it's going to, or is shorter than BP. If AP is shorter than BP, then it's going to be inside this circle. So AP shorter than BP implies inside the circle. Okay, and AP being longer than BP, sorry, shortest side nor the longest side. So AP being longer than BP. Sorry. Let me get my thoughts straight. This should be AB, not BP. And that's the maximum size it could be. And AP larger than BP means that it's to the left of the line. If these are midpoints right here. Okay, so we have some cases. Here, wait, but this would be larger than BP. So inside the circle, but right of the line. And then here, AP, AB, this would be left of the line, but outside circle. So what we basically need to do is, if this was a square of area 1, then we just need to find, or side length 1, then we need to find the shaded region that I've just identified. So here, this is a sector of radius 60 degrees. Right here, because this is an equilateral triangle, and this is, this is half of this, and this is a right angle. So this is a 30, 60, 90 triangle. This is 60. So the area of this piece right here is going to be pi over 6 minus root 3 over 4 is the area? Question mark? No, root 3 over 8 is the area. Okay, so that's this region right here. Pi over 6 minus root 3 over 8. Now we need to find this region. That is going to be 1/2 minus pi over 4 minus this piece right here. So pi over 6 minus root 3 over 8. So that is 1/2 minus pi over 4 plus pi over 6 minus root 3 over 8. So this is 1/2 minus pi over, why do I want to say 12? I want to say 12. Minus root 3 over 8. So we have 6 minus pi. Oh, not 6. The GCD of 12 and 8 is 24. So we have 12 minus 2 pi plus 3 root 3 over 24. I think that is good. So then we have, let me just make sure that I have all my numbers correct. Six, wait, that's 1/2 minus, 6 plus pi. Why do I have 12 over 24? This is a 4. How did that become a 4? All right, let me just check my notes real quick. Sorry for the interruption, guys. This is embarrassing, but it's got to be done. Oh, we have to add these cases. Sorry, we have to add these cases together. Okay, so we have 1/2 minus pi over 12 minus root 3 over 8 plus pi over 6 minus root 3 over 8. That is 1/2 minus pi over, or plus pi over 12 minus root 3 over 4. So then finally putting all that together, we have 6 plus pi minus 3 root 3 over 12. So then we have 6 plus 1 plus 3 plus 3 plus 12, which is 25. So it's A. Sorry, I'm going a little fast. We still have 10 more minutes. I have to choose which one I want to do.
Can you leave
I
24
can't.
for a
I'm
little-
sorry. I'm sorry. I can't. Let's.
你do screenshot 不就好了？
There's also going to be a recording available. So let's do problem 20. A silo, which is a right circular cylinder with diameter 20 meters, stands in a field. McDonald. No, I'm actually going to want something larger than that. So McDonald is standing 20 feet away from the center and east of or west of the center and 15 feet south of the center. Right? And if we take the line of sight, so this is 10, this is 10, this is 20, sorry. The line of sight, McGregor is located 20 meters east and G greater than 0 meters south of the center of the silo. The line of sight between McDonald's and McGregor is tangent to the line of the silo. The value of G can be written as the square root of B minus C over D, where A, B, C, and D are positive integers. B is not divisible by the square of any prime, and D is relatively prime to the greatest common divisor of A and B. What is A plus B plus C plus D? Let's try to find this out. In order to do so, I'm going to draw a bunch of line segments here. Okay, because we're going to use some similar triangles. So first of all, from the Pythagorean theorem, we know that segment AE is equal to AO squared plus OE squared. Then, pardon me. I need to label these, sorry. And let's move this over here. So this is A, B, O, C, D, F, and E. And this is a tangent line, so it's perpendicular there. So we know that AE is equal to AO squared. Sorry, that should be a minus OE squared. Oh, wait. Put on the annotations back. And we know that AO squared is equal to AB squared plus BO squared. So AE is equal to, that's going to be 15 squared plus 20 squared. That's 25 squared minus OE squared. Okay, but OE is actually 10. So this is 625 minus 100 is equal to the square root of 525 is equal to 5 root 21. All right, and DE by the same logic is equal to the square root of DO squared minus OE squared, which is equal to the square root of CD squared plus CO squared minus 10 squared, which is equal to 300 plus G squared. I know I'm going fast. I'm sorry. I'm just trying to finish all of this as much as I can. So AH, oh, sorry, let's drop this height right here. Call this H. Let's call this is still G, so this is 15 minus G. Now, AH is equal to 15 minus G. So triangle ADH is a right triangle. And so we get that this length plus this length squared. So 5 root 21 plus the square root of 300 plus G squared. That should be equal to 40 squared plus 15 minus G squared. Now, I have already done a lot of algebra rearranging equations like this into a quadratic. So I am going to skip some algebra, and we get 12G squared plus 600G minus 3,700 is equal to 0. Or G is equal to minus 75 plus or minus 20 root 21 over 3. Taking the positive root, G is equal to 20 root 21 minus 75 over 3. And so I think that's it. We have 20 plus 21 plus 75 plus 3. And that adds up to 119. All right, we got one more question left. We got 4 minutes. I'm not sure we have enough time to solve it in 4 minutes. So if you want to stay late, you can watch me. I will be here. And yeah, so triangle ABC has side lengths AB equals 80, BC equals 45, and AC equals 75. So ACB, here is 75, here is 80, here is 45. Interesting comments being left. So for 23, let's draw. Oh, let me read it. So triangle ABCD has side lengths AB equals 80, BC equals 45, and AC equals 75. The bisector of B and the altitude to side AB intersect at a point P. What is BP? All right, so I'm just going to be doing a ton of algebra. You're going to have to forgive me that it's going to take a while. So we know, let's call this point D. So, and it's perpendicular. Oh, sorry. This point is D right here. So we know that AC squared is going to be equal to AD squared plus CD squared. And BC squared is going to be equal to BD squared plus CD squared. And so that means that AC squared minus BC squared, sorry, I put the squared in the wrong spot here. That is equal to AD squared minus BD squared. Some of these values are known to us though. This is equal to AD minus BD times AD plus BD. So we get AD plus BD, well, that's just 80. So 80 times AD minus BD is equal to this expression. However, AC squared minus BC squared is 75 squared minus 45 squared, which is equal to 3,600. So that is equal to, or that tells us that 45 is equal to AD minus BD, right? Let me just make sure I'm not getting that wrong. Yeah. And again, similarly, AD is equal to AD plus BD. So, and then we have 45 is equal to AD minus BD. And with that information, we can determine that AD is equal to 125 over 2 and BD is equal to 35 over 2. All right, and so CD squared, which is AC squared minus AD squared, that is equal to 75 squared minus 125 over 2 squared. So CD is equal to 25 root 11 over 2. Now, according to similar triangles here, we are going to have that, no, sorry, according to the angle bisector theorem, which comes from similar triangles, I guess, but we don't need to go that deep. So DP over PC is equal to DB over BC. So 35 over 2, what are my notes saying here? PC what are my notes saying? Oh, okay, so we have 35 over 2 right here, and BP is or sorry, PC is 45. We just got that somewhere. Oh, no. So it's just DB over BC, which is 35 over 2 over 45, which is 7 over 18. So we also know that PC is equal to CD minus DP. And if we rearrange this equation, then we get 18 times DP is equal to 7 times C minus DP. Running out of space here. And let's see. Seven over. Oh, we can just rearrange this again. So we get 25 dp is equal to 7 cd with this. So dp is equal to 7 over 25 times cd, but we already found cd. dp is equal to 7 over 25 times 25 root 11 over 2. I'm going to switch colors. So here we have this comes out to comes out to 7 root 11 over 2, and so I'm unfortunately going to have to erase some of this. I'm going to erase these two. We know that BP squared is equal to BD squared plus DP squared is equal to 35 over 2 squared plus 7 root 11 over 2 squared, which is equal to 1,225 over 4 plus 49 times 11 over 4, which is equal to 1,764 over 4, which is equal to 441, which is 21 squared. So BP is equal to 21, which is D. Wow, that was a lot of work. That one, I think, in my opinion, was the hardest problem on the test. Does anyone have any questions about any problem? Would they like me to go back to any of them? I'm happy to stick around while people need help from me. Otherwise, you're free to go. If you had a ruler, you could draw it out. I wouldn't try to do that. Later, Martin. It was 21, yeah. I don't know. I don't think about that kind of stuff anymore. I'm almost 30 years old. I just think about how to do the math. I figure as long as you try your best, then you're either going to get the Amy or you're not. But there's really nothing you can do or worry about besides just your best. Later, everyone. Thank you. Have a good one. Enjoy your time. You're welcome. Thank you for showing up. Yeah, thank you for listening. All right, you have a good one.